Hello, my name is John Moyer, and I want to welcome you to the NIH Office series. This series explores research design, measurement, intervention, data analysis, and other methods of interest to prevention science. Our goal is to engage the prevention research community in thought-provoking discussions to promote the use of the best available methods and to support the development of better methods. Before we begin, I have some housekeeping items. You can submit questions during the webinar via the chat pod. You'll need to open the pod by clicking on the chat icon located in the lower right-hand corner of your WebEx window. Please direct your questions to all panelists. We will open the floor to questions that have been submitted via WebEx at the conclusion of today's talk. The slides and video recording will be posted on our website, prevention.nih.gov/mindthegap, in approximately 2 weeks. You will receive an email when they are available. Lastly, we would appreciate your feedback about today's webinar. Upon closing the WebEx meeting, you will be prompted to complete an evaluation. We would appreciate your feedback as it will help us improve this webinar series. At this time, I'd like to introduce Dr. David M. Murray, Associate Director for Prevention and Director of the Office of Disease Prevention.
Thank you, John. I'm very happy to introduce today's speaker, who is Dr. Rebecca Andridge. Dr. Andridge is an associate professor in the Division of Biostatistics at The Ohio State University in the College of Public Health. Her research is focused on imputation methods for missing data, primarily in large-scale probability samples and in group randomized trials, and when missingness is driven by the missing values themselves. She collaborates with researchers across the Ohio State campus, including the Institute for Behavioral Medicine Research, the Nisonga Center, which is a university center for excellence in developmental disabilities, and the Comprehensive Cancer Center. In addition, Dr. Andridge teaches introductory graduate and undergraduate biostatistics and was the 2011 winner of the College of Public Health Excellence in Teaching Award. She's an elected fellow of the American Statistical Association and really a terrific biostatistician. I will take a little credit for her since I recruited her to Ohio State as a brand new assistant professor. It's my pleasure to welcome Dr. Andridge.
Thank you, David, and thank you for the invitation to speak in this Mind the Gap series, which is a phenomenal resource for researchers. So today I'm going to be talking about multiple imputation methods for group-based interventions. So there's two obviously big chunks in this title: multiple imputation and group-based interventions. So I'm sort of going to assume that a lot of the people on this call know a little bit about group-based intervention trials, although I'll briefly talk about those, and really spend most of the time focusing on an introduction to multiple imputation and how to do that correctly when you have data from group-based intervention trials. So I'll start by describing what missing data look like in this type of trial, and then how can you handle it with multiple imputation? When should you use multiple imputation? How do you correctly use multiple imputation? And then share some resources of software where you can actually use these methods. So we'll start with missing data in the group-based intervention trial framework. So randomized trial designs for group-based interventions, the three kind of big buckets are listed on this slide. The cluster randomized trials, or CRTs, where you're randomizing groups, often in parallel, right? A parallel design. Some groups, some clusters or groups are on some sort of placebo or control, and the others are given a treatment, and you follow them over time. Alternatively, we can have individually randomized group treatment trials, or IRGTs, where you randomize at the individual level, but the intervention is delivered in a group. So small groups of people receive the intervention, and that essentially creates groups by virtue of how you're delivering the intervention. And then finally, a more recently popular method is the stepped wedge cluster randomized trial. The stepped wedge is like a cluster randomized trial where groups are randomized, but they actually don't run in parallel. And instead, these clusters or groups sequentially transition from being on the control to the intervention as you move through time, and they're measured in each time. So some of the advantages of these kinds of designs, I'm sure many people listening are familiar, things like reducing treatment contamination, there could be lower costs, you can test an intervention that can't be randomized at an individual level. In the case of a stepped wedge, by the end, you've given the intervention to everyone, so there could be sort of some ethical considerations. There are a lot of reasons why these kinds of trials are popular. So as a result, the data that come out of these kinds of trials, we have a small, usually, number of groups or clusters with correlated observations within a group. So when we have clusters that have been randomized, usually there are characteristics of those clusters that make people in the cluster more similar than within the group than they are to people outside of the group. So the classic example I like to think of this is schools or kids in schools. So kids within one school are going to be more similar to each other than kids in another school based on the fact that they live in a similar area, etc. You also, in the case of the individually randomized group treatment trial, might be delivering the intervention in a group. And so you might be causing what we think of as sort of more similar intervention effects within the group. So imagine something that has to do with group therapy. And so they're being led by an interventionist, and there could be different interventionists, and sort of how strong of an intervention effect you have might be related to who's leading the group and also the dynamics of the group. So there's going to be sort of more similar outcomes within those clusters. As a result, this correlation is called the intra-cluster correlation or the interclass correlation, ICC. It is usually not that big. It's not as high of a correlation as if you measure an individual multiple times, right? But it can lead to very large variance inflation factors, and you cannot ignore the fact that you have this clustering. So from the survey sampling literature, we have this concept of the design effect, which is sort of how much bigger is your variance, right? That measure of variability if you use this design relative to if you could have done everything at the individual level, if there were no correlations. And the formula here shows 1 plus m minus 1 times rho, where m is the size of the cluster and rho is that ICC, that correlation. So even if rho is small, in a cluster randomized trial or these other designs, M is usually pretty big. So if, for example, M is about 100 and rho is small, 0.01, that's a really small correlation, you still get a design effect of almost 2. So you have twice as big a variance as you would have if you could have had individuals who are independent. So clearly you can't just ignore that, right? You're going to be way underestimating your variance if you ignore the fact that these people were clustering. And as a result, you're going to get p-values that are much too small and inflate your type 1 error. So how do we analyze data from this type of trial? So this is important to think about because if we have missing data, we need to think about how to accommodate that, and it depends on how you're going to analyze it. So there are two basic approaches: cluster level analyses, in which you basically remove the correlation by using summary statistics. So think of it as taking the mean for each cluster. Well, now you have cluster means, and the cluster means are independent. So you could do, let's say, a 2-sample t-test if you had 2 treatment arms. That is not a super common method of analysis, although it is done. More common are individual level analyses. And the two most common approaches are mixed effects, also called random effects models, and generalized estimating equations. And the difference here is that in a random effects model, you are explicitly modeling that correlation, the ICC, via something called random effects, right? They usually have normal distribution. You essentially write down an equation that explicitly says, I want to estimate this random effect and the size of this correlation. In the generalized estimating equations, we say, okay, we acknowledge there's a correlation, but we don't really care about the estimating that correlation. It's a nuisance. So we acknowledge it, and we used what's called robust inference that basically accounts for that correlation, but we don't, and in fact, often even get an estimate of that correlation. We just essentially kind of wiggle it away. So if you have complete data from all your participants in all your clusters and both of your treatment arms, all of these methods are going to be appropriate, right? You can pick them, do any of these, you're going to get the right answer. However, if you have missing data from some participants, some of these methods may not be appropriate except under some very strong assumptions. So that's, of course, what I'm going to be talking about today. So in the CRT framework, there are 2 general types of missing data that you can have, right? You could have individuals with missing data. So that's this, on the side here, we see the second row is this individual is missing all 3 of these variables, X, Y, and Z, whereas this last person in cluster 1 is only missing the X variable. So that's individual level missing data. But you can also have entire clusters with missing data. So down here, we see cluster 3. We just completely lost all the data for that cluster. This is actually more common than I would like to believe when I started to looking into this, especially trials that take place in other countries. Sometimes entire clusters, entire villages will have to drop out of a study. So we can have entire clusters with missing data. So this is something that is unique about this CRT and this cluster design, is that you get these 2 different types of missing data. Whole clusters missing is an enormous challenge. And I am, in fact, not going to talk about that in the rest of this. I'm going to focus on individuals with missing data. In addition, we have two types of variables that can be missing: individual level variables and cluster level variables. So on this slide, the only cluster level variable I have illustrated is treatment, right? So the treatment group is the same for every member in a cluster. Oops, that's a typo. That should clearly be a 1 right there. Should be the same. But you can also have individual level variables here, obviously X, Y, and Z. So I'm going to focus on missing individual level data. It is less common to have missing cluster level data and entire clusters of missing data, but that does happen. But that's a whole other webinar, how to handle that type of missing data. So when we talk about missing data, statisticians tend to throw around a lot of lingo. So we'll start by going through some of those words we use, some analysis strategies with missing data. First of all, one I know everybody has heard, you've read it in a million journal articles: complete case analysis. So in a complete case analysis, you only use the observations that are complete with respect to all variables. So on this slide here, I have grayed out any observation in this little data set that would not contribute in a complete case analysis. Doesn't matter which variable is missing. If there was a question mark, I've grayed you out. So only the non-grayed out observations would contribute in a complete case analysis. In an available case analysis, you actually use observations that are complete with respect to the variables you're using in your analysis. This seems like a subtle difference, but it is an important one. So here I've highlighted on the right here, column Y. Suppose we were just looking at this Y variable. That's our analysis variable. Well, this individual here in the bottom of cluster 1 has X missing, but has Y. So that person gets to contribute to this analysis. If we were analyzing X, that observation would be removed, right? We would not be using that observation. So it's a subtle difference, but it's important because available case analysis is actually what statistical software does by default. If you were using, let's say, SAS, and you were running some regression models, and you ran a regression model that used just Y, this person would be included. And if you added X in as a predictor, that person would suddenly be excluded. So the number of individuals in your two models would actually be different. So when we talk about missing data, most of the time, when we write about it, people say complete case, they really mean available case. They kind of mean complete case with respect to one particular analysis that I'm running. So that's a little bit of a tricky subtlety. And then finally, imputation, which is what I'm going to spend the most of my time today talking about, which is when we're going to fill in those missing values to create completed data sets. So instead of having to strike out these observations with the question marks, we're going to use some kind of a technique to fill in those question marks with numbers. So we're going to replace those missing values. So more lingo in the missing data world, which may be familiar to some people listening, are the taxonomy of missing data. So we'll start with the best case scenario, missing completely at random. So when you have data and you have missing values and you believe that they are missing completely at random, that means that the probability that that variable that you see has missing values doesn't depend on any variable, including itself. Essentially, think of that as completely random. I always give the example of I'm carrying my data in my arms and I trip and 10% of it falls down the gutter. Totally freak accident, completely random that 10% of my data are now missing. That is missing completely at a random. And if we think about the individuals in and out of an analysis with the missing data and with complete data, there's no distinguishing feature that you can tell them apart. Right? It's as if you flipped a coin and said, is this person going to have missing data or not? This is the best case scenario. But as you can imagine, with my somewhat silly sounding examples of flipping a coin or dropping my data in the gutter, this is often not a realistic assumption. More realistic is what is called missing at random. So missing at random means that the probability that you have a missing value depends on another variable that you observe, right? So it could be that the probability that someone reported their income was higher for older people than younger people. So older people more likely to report their income than younger people. If I observe everybody's age, then income is missing at random. The thing that drives the missingness, the feature that drives the missingness is observed for everybody. It's not missing. So the people in my analysis, if I did complete case versus out of my analysis, they're different, right? Because I'm going to have more older people in my analysis if they're the ones who reported their income, but I can see how they're different. So you can think of that as better because I can basically adjust for that difference, right? I can take into account the fact that I know that I have a biased sample and that I'm going to have more older people because they're the ones who reported their incomes. So this one in the middle, missing at random, gets the smiley face instead of the big star face. Unfortunately, there's a worst case. The worst case is missing not at random or not missing at random. In this situation, the probability a variable is missing depends on the values of something you don't see. The classic example is, in fact, income. Because when it comes to reporting income, we believe that people with certain levels of income are less likely to report their income. So it's more likely to be missing. So it isn't really that older people are more likely to report their income than younger people. It's really that people who make less money are less likely to report it than people who make more money, or perhaps vice versa. But since I don't observe your income, if you don't give it to me, I don't see that thing that makes you different, the person with the missing data versus the person with the observed data. So we don't know how these two groups of people are different, my complete cases and my cases with the missing values of income. So this is unfortunately the worst case scenario, and it is believable in some scenarios, and in the survey world, it's 100% believable for certain characteristics like income, in addition to some other things you can imagine, things like drug use, right, socially undesirable behaviors, or self-reporting of those things. So the biggest problem with this taxonomy, or not problem, but what this lets us see, is that you cannot distinguish between the middle column, missing at random, and the rightmost column, not missing at random, with your data. There's nothing in your data that can tell you which one of those two you have. You can distinguish between MCAR and MAR, but you can't distinguish between MAR and MNAR. So what ends up happening most of the time is people make the assumption of missing at random. And most of the time it is probably pretty plausible, and there are things you can do to make it more plausible. I'll talk about those in the imputation section. But we always have to consider this fact that not missing at random could be plausible. If you're testing a treatment, it could be that the people who have the worst response to the treatment don't come back for their follow-up. But you won't know that because you don't measure them because they don't come back. So not missing at random is in some cases plausible. And the only thing you can do is do sensitivity analyses in order to kind of tease out, make different assumptions and see what might be the answer. So let's turn to CRTs. What are people doing handling missing data in cluster randomized trials? So there's a systematic review many years ago now, in 2016. It looked at a random sample of 86 CRTs. Nearly 1/3 of them had entire clusters missing. So there's my double exclamation point, because that is shockingly high to me, right? Entire clusters missing, especially since that's a really hard thing to deal with. The majority of them reported at least some individual level missing data, right? So over 90% said, yeah, we didn't get complete follow-up data on every individual in every cluster. And the median was 19% of the subjects missing the outcome. The plot that I've excerpted from this paper on the right shows the percentage of individuals with a missing outcome. That hideous, ugly little blip tail at the end there is 80 to 90%. So unbelievably, there was a trial where, you get 80% of the people missing the outcome at the end. Complete case analysis was the most used method. It was, I suspect, really available case analysis, but sort of semantics. Essentially, they're going to just discard everybody who doesn't have that outcome measured at the end of the trial and only analyze those who have the outcome data. Only 2% of the trials, and now this was in 2016 that they were looking retrospectively at trials, used multiple imputation. Multiple imputation has gained in popularity. I suspect if this review were done again, it might be slightly higher. But neither of those trials was 2 trials, and neither of them actually implemented the multiple imputation correctly. So there's an issue here. It's that people don't know that complete case isn't always the best answer, and perhaps don't understand how multiple imputation can be helpful and when it should be used and how it should be used correctly. So let's talk about multiple imputation. What is it? Well, we'll start with what is it not? It is not trying to exactly replicate unobserved data values. My goal with multiple imputation is not to figure out exactly what those question marks really would have been if I had observed them. I'm never going to know that unless I can somehow go round up that participant and badger them into giving me their response, right? So that's not what multiple imputation is trying to do. What it is it's attempting to use all the available information in your data to figure out what maybe those missing values might have been. because if I have missing value for a person for one characteristic, but if I know a lot of other things about that person, I have some information about what that missing value might be. Multiple imputation is most useful when you have good predictors of missing data values. So like I said, this idea of having good information about a person that could inform what is that missing value that you don't have. It is flexible and adaptable for different data types. So continuous variables, nominal variables, binary variables, right? There are different flavors of multiple imputation for different data types. It can be used when you have missing outcome or covariate data, or both. So it is not just limited to one or the other. Basically, anything that's missing, we could use multiple imputation. It is usually assumed under a missing at random assumption. So we are going under the assumption that there is not that horrible, awful missing not at random. The value is missing because of what the value is I don't see. We assume we have essentially information around the missing value with which we can impute correctly, right? We can rely on that assumption. But multiple imputation is not necessarily the best solution for a randomized trial, and I'll expound on that. So these are all the sort of things to think about when we think about multiple imputation. In actually implementing multiple imputation, we have three phases. It starts with the imputation phase. So you have a data set with missing data, and you're going to essentially replicate that data set, capital D times. Here on this image, I'm showing 20, up to 20 times, and fill in the missing values using some kind of an imputation procedure, D different times. And each time you're filling in the missing data, it's some kind of a draw from a predictive distribution of the missing values. I'll show you an illustration. Then, once you have completed your data sets, you analyze each data set separately. This is why people like multiple imputation, because the analysis you do is the same analysis as if you had complete data. So if you have a CRT and you do multiple imputation correctly, each one of these analyses with each of your data sets could be, let's say, a random effects model with a random intercept for cluster, right? It's what you would do if you had complete data. So that's a very attractive feature of multiple imputation. And then once you have all these capital D estimates, because you've done this capital D times, you combine the results in what's called the pooling phase in a relatively straightforward way. And this methodology is attributed to Don Rubin, and this is his book in 1987. I want to note that this reference down here at the bottom where I have kind of adapted this figure, Enders. It's an excellent textbook. I'll show you the citation for it again if you're looking for a gentle introduction to missing data analysis. So how do we actually do the combining? If I have an estimate of some parameter, let's say it's a treatment effect, right? It's the regression coefficient for the treatment group indicator in my random effects model, right? Where I look at the cluster or the overall treatment versus control estimate. I have D of them. And then each one of those from my model that I ran on each of my imputed data sets, I have an estimate of the variance of that theta hat D. So overall, what's my estimate of the treatment effect? I just average across my D data sets. That seems pretty standard, right? I've got D different data sets that I've filled in. I take the average treatment effect. The average of those point estimates is my multiple imputation estimate of the overall treatment effect. The variance is a little bit more complicated, but it actually makes sense. So starting down here with WD, big WD, this is the within imputation variance. It is just the average of my variance estimates from each of my D data sets. So I got out my treatment effect and its estimated variance. I average the treatment effects for my estimated treatment effect, and I average my variance estimates to get my average within imputation variance. But that's not the only variability present, because theta hat D is different in every data set. So if we think about the variability of those theta hat Ds, that's the between imputation variance. How much variability is there from imputed data set to imputed data set? This is literally just the variance of those D estimates. That's the between imputation variance. So my total variance that I have to account for after doing multiple imputation is the sum of those two things. The within imputation variance plus the between imputation variance. There's a little bit of an extra inflation here for the fact that we do a finite number of imputations, but effectively what we're doing is adding the within imputation to the between imputation variance. And if we want to do inference, we use the T distribution, and the degrees of freedom for the T distribution depend actually on those two different components, the within and the between. And importantly for CRTs, there's a small sample correction that needs to be used when you're not going to have very many degrees of freedom for your, if you had complete data. right? So if you had complete data and you were looking at the treatment effect, your degrees of freedom would be based on number of clusters. So that's going to be a small number. So there's an alternative formula that software will calculate for you when you have a small number of degrees of freedom. So here's just a little kind of toy example of what multiple imputation looks like. There's my y with 3 question marks and my helpful extra variable z. I'm going to fill in y for my first imputed data set, and I get out an average value of 16.93 and its estimated variance of 1.85. And I do it again. I get different values imputed. I get a different average, and I get a different estimated variance. And then I do it again. So here I've done 3 imputed data sets. My estimate of the overall mean of y is just the average of these means. And my estimate of the variance comes from the between imputation variance, the within imputation variance, and summing them. So notice that my total variance is bigger really than any one of my individual variance estimates from any of the 1 imputed data sets, because no one imputed data set is the truth, right? I have to account for the fact that I've done this random imputation. So some other things to think about with multiple imputation. Imputations must vary across the multiple imputation data sets, right? It's not deterministic. You're not filling in the same value each time. There's going to be variability across the data sets. Imputations must be what's called proper for correct inference. I'll talk about that in a moment. Imputations can come from implicit or explicit models, and the imputation model must be congenial to the analysis model. Again, I'll define that in a moment. So proper MI, I've got some little proper numbers in their formal wear up in the corner here. What is proper multiple imputation? Well, the idea of proper multiple imputation is that you must propagate the uncertainty. You are filling in missing values that you don't know. And you're using a model from data that's collected that has sampling error. You need to continuously think about how much variability there should be, right? You shouldn't just be filling in one number and believing that's the truth. There's going to be variability. So this is a little illustration. The black dots here are the observed data points. The blue line here is a regression line fitted to those data points. And down here on the bottom with the red marks are the places where I have missing values. So I'm missing my y and I have my x. And I want to fill in my y value. Well, naively, I could just predict from a regression equation, right? What is the y hat? Where are they along the line? But that's certainly not propagating uncertainty. That's pretending that your regression equation is exactly right and that there's no residual error for those observations. So instead, I could wiggle those observations. Okay, that's a little bit better. We've got the error, but the problem is that that regression line also has variability, right? Because if you took a different sample, you would get a slightly different line. So the better is to also be thinking of drawing or wiggling that line and having the regression or the imputed values be coming out of that with some error. So it's that idea of everything you estimate is inherently uncertain. So we need to propagate that through multiple imputation. So this is why one of the reasons things like a mean imputation is not proper. It's not properly getting that uncertainty. The other word that's important in multiple imputation is congeniality. So congeniality is talking about the relationship between 2 different models. We have the imputer's model, so that's what model am I using to fill in the missing values, and the analyst's model. What model is the analyst, who may or may not be me, using to answer the scientific question? So in the case of the CRT, maybe it's that random effects model with the indicator for treatment. A congenial imputation model is consistent with or compatible with the analysis model. So it's about congeniality, is about the friendliness of these 2 models. Can the analyst model be derived from the imputers? So I might use a whole bunch of variables to impute, and the analyst might actually only use one of those in their model, but that's okay because mine is bigger, right? My model, the imputer's model, is bigger than the analyst model. That is okay. That is congenial. If, however, if I ignore treatment in my imputation model, and then the analyst has a treatment indicator in their equation that's their model, that's a problem. That is uncongeniality because my model is not more general than, right? It's not a big broader version of the analyst's model. So this congeniality is a problem for all types of multiple imputation. And in group-based trials, it can arise in some standard and sort of less standard ways. So some sources of uncongeniality: omitting important covariates, like the example of treatment indicator. Right, the second bullet, not including the treatment indicator. You have to include that when you're doing your imputation. Not including outcomes when you're imputing covariates. A lot of times people think it's weird to impute a covariate using the outcome as a predictor, but that absolutely has to happen, or else you're going to attenuate associations. Leaving out interactions, if they exist, can cause uncongeniality. And I have bolded here ignoring clustering, because this is the big problem with group randomized trials and imputation. And it's what was wrong with those methods that were used in the Fierro systematic review, where I said that the 2 trials that they found did imputation incorrectly. So as a sort of side note, there are 2 main types of multiple imputation: joint modeling and fully conditional specification, which also goes by a billion other names, including mice and SRI. In a joint model, you build one gigantic statistical model and simultaneously draw all the missing values from this big multivariate distribution. And in fully conditional specification, you essentially impute variables one at a time. Think of it as running a regression model for each variable and imputing from it, right, sequentially and iterating. These 2 methods give you the same answer with single level multivariate normal data, but not other types of data, including the multi-level data in CRTs. So it is important to just keep this in the back of your mind, because different software packages will offer different options. So let's get to when should I use MI for my group-based intervention trial. So I wish the answer were, you should always use MI, but in fact, the answer is not, you should always use MI, because sometimes a complete case analysis is okay. A complete case analysis is going to give you unbiased estimates of everything if your data are MCAR, missing completely at random. If I accidentally drop 10% of my data, doesn't matter what variables are missing, if I subset to the complete cases or the available cases, I'm going to get the right answer. I'm going to have a pretty big error if I lost a lot of my data, right? My standard errors are going to be bigger than I'd like them to be, but I'm going to get an unbiased estimate. It also, importantly, is okay for a regression coefficient if it's the outcome that's missing, and missingness depends on X. So if I have a predictor variable that's going to be in my regression equation and it predicts missingness in my outcome, then I actually get the right answer with a complete case analysis. Importantly, in the context of a randomized trial, if missingness in your outcome, right? So some of your people, you couldn't measure them. In some clusters, you get some individuals, so you couldn't measure Y at the end. If the missingness depends only on something you observe, a baseline covariate X or a treatment assignment T, and we assume we have complete data on both of those, then a complete case analysis will give you unbiased estimates in this regression equation that has both T and X in it. So I don't actually need to do multiple imputation. If I am confident that these are the 2 variables that are predictive of missingness in Y, and Y is the only thing that has missingness. So I don't need to do multiple imputation all the time, right? In a randomized trial, we're likely to have completely observed treatment assignment and a bunch of completely observed baseline covariates. So this assumption, it happens in randomized trials. If you went and did multiple imputation, you're going to get the same answer as complete case. It's just with a little bit of error because there's randomness in multiple imputation. So there's no need to do multiple imputation in this particular case of this regression equation with missingness in the outcome only. So when do we want to use MI? Well, if you believe that your data are missing at random, not MCAR, which is almost all the time, we believe MAR, not MCAR, and maybe you don't want to have X in your analysis model. So your analysis model doesn't look like this, right? You don't want X here, you just want T. Well, then you could use multiple imputation, use the X information to impute Y, but then don't have it in your model, right? And so that then multiple imputation would be an appropriate use. What if you want to use all randomized participants in the analysis? So some people have argued that this is necessary for an ITT analysis, is that you need everybody to be in there. And so maybe you need to fill in the missing outcomes. Or maybe you have some missingness in X, and that's less likely for baseline covariates. So in CRTs and IRGTs and step wedge designs, often the analysis model is specified a priori, and sometimes we don't have those covariates. And so then if we end up with missing Y, we want to use imputation in order to ensure that we get unbiased estimates. And multiple imputation is a sensible approach. But the issue is, how do you use it correctly? Here are 2 uncongenial strategies, and these are important to consider because they're easy ways and they're wrong. So the first is to just ignore the clustering, and I'm sure everybody on this call could guess that that's a bad idea. And what happens is you get variance estimates that are too small, and it's worse the higher the clustering within the higher the ICC within the cluster. So your p-values are too small. It's anti-conservative. Alternatively, you could include fixed effects for clusters. So it's like an indicator for each of your clusters, right? Each cluster getting a separate intercept, a fixed intercept. But the problem with this strategy is actually the reverse. your variance estimates are going to be too big. And it's going to be worse with smaller ICCs. So the tinier your ICC is, the worse the problem is. You're going to get p-values that are too big. So it's anti-conservative. And how bad are these methods? Well, they're not good. So suppose I have this very basic setup, K clusters, M individuals per cluster. The true data come from this random effects model. The important component here is rho, the ICC, and I have pi units with observed data in each cluster. So let's say 80%. If you ignore the clusters, you get a negative estimate of the bias. This is always negative because of this term right here, and rho is at the top. The bigger the correlation, the worse the bias. If you use fixed effects, it's the reverse. 1 minus rho is in the top, so the smaller the rho, the worse the problem, and it's always positive. So this is this sort of competing badness in opposite directions. So here's just a plot of the relative bias. The black line is where you want to be. So if I have 10% missingness and I ignore the clustering, as the ICC goes up, I can get down to about 15%, negative 15% bias. So I'm underestimating the variance by 15%. And of course, with 50% or 30%, it's much worse. Notice it gets bad pretty quickly with these ICCs. And this is a type of, these should say 0.05 and 0.01, I'm just realizing. Down with fixed effects for clusters, it's the reverse. It's worse when you have an ICC near 0, right? This is a doubling of variance, right? That's really bad. I mean, that would 50% missingness is a lot, but that's really bad. So these strategies are definitely not appropriate. Although I would argue if you had to use one of these, fixed effects is better because it's conservative, right? As opposed to increasing your type 1 error. So what is the right way to do it? Well, congenial strategies. Use the model you're going to use for your analysis. That's the mixed model with a random intercept for cluster. It's a specific type of multi-level multiple imputation. It is available in software packages. Unfortunately, it's not available in the software packages most people use. It's sort of available in more specialized software packages. Or with a student, I have developed a new method, predictive mean matching for CRTs, that relaxes the model assumptions. So it sort of reduces the reliance on estimating the random effects, but it's not available in software. You have to get the code from my student. So I'm just going to show you how this works with an illustrative CRT. It's a health education for hypertension that took place in South India. I did not work on this project, but the data were made publicly available by the authors. And so for that, I am very grateful. The intervention was a community health worker-led program, and the control was usual care. The clusters were villages. There were 5 on intervention and 10 on control, and they were, decent in size. The total sample size just shy of 2,000. The primary outcome was control of hypertension measured about 2 months post-intervention. The follow-up did have missing data. It was about 15% missingness overall, but it was differential between treatment and control. So there's actually a lot more missing data in the treatment group. So right away, we know this is not missing completely at random, because it's dependent on treatment group. So group is a predictor of the missingness, so it must be at minimum missing at random. And we have some evidence against missing completely at random. In addition to that, if we compare the people who had observed, who were complete cases versus incomplete cases, the people who did not contribute data at the end had higher systolic blood pressure. They were less likely to be using medication. They were more likely to have never had an MD follow-up, and they were more likely to be male. So there's definitely observable differences between the people who contributed data and those who did not. Importantly, these variables are also associated with the outcome. So the details of this slide aren't really important, just to note that systolic blood pressure, using BP meds, et cetera, is associated with how well the intervention worked among those people for whom we observed the follow-up. So if I do a complete case analysis, I can run lots of different types of models. I'm using a complete case only, mixed effects model, focus here on the unadjusted model where treatment group is the only predictor in the model, and we get an estimate of a decrease in systolic blood pressure of 6.5 points. And it is significant. If I do multiple imputation, I'm actually going to impute the follow-up baseline systolic blood pressure and then calculate the change score. And I can do it in lots of different methods. The correct method, random intercept for clusters, returns a treatment effect that's pretty similar to the complete case. And the ICC is actually pretty similar. 0.049 was 0.048 over here. If I ignore clustering and do the imputation, I get a similar treatment effect, but I get a smaller ICC, right? As the theory says should happen. And if I use fixed effects for clusters, again, a similar treatment effect, but too big of an ICC. In this particular instance, this is a pretty substantially successful in terms of a significant effect treatment. So it doesn't change, the p-value is not crossing the threshold with any of these different analyses, but the only correct one is the random intercept for clusters. So as a warning, effect modification is something to be concerned about when we're thinking about imputation. And if we have some baseline covariate that is a treatment effect modifier, it needs to be in the imputation model as an interaction. So the safest way to do this is to separately impute by treatment arm. So take your clusters that got treatment and impute for them. Take your clusters that got control and impute for them. But this can be really problematic for a group-based trial, right? In this example, there were only 5 treatment clusters. That's going to be hard for estimating random effects. So this could be challenging to implement with cluster randomized trials. Much easier with an individually randomized trial. So just to wrap things up, I'm just going to kind of tell you what are the software that you can use for multiple imputation and group-based trials to do it correctly. The one I use the most is R. So R is freely available software for multiple operating systems. It has a lot of different implementations of correctly implemented multiple imputation for multi-level models, right, for CRTs. The mice package is probably the most oftenly used one. Despite being called mice, so it's the multiple imputation by chained equations, that's the sequential version, but they do actually have options that are joint model based in addition to the sequential imputation. I want to highlight this online version of a textbook that it includes the R code, so just walks you through and what's going on. It's an excellent resource by the author of this package. And then there are several other packages that do different flavors because R is open source, so anyone can write their code to do the imputation. But these are vetted, I'll say, implementing it correctly. So R is not as user-friendly as SAS or Stata or those big companies, but the help files are usually helpful, and I recommend the use of RStudio as a GUI, a graphical user interface. There is also a relatively new, powerful free software called Blimp. It is also associated with a textbook. This is that textbook I was referencing before. This is the 2nd edition. It's not quite out yet, but it comes out in August. But it also sort of integrates how to use their software with the textbook. It's available for multiple operating systems. It does do FCS imputation, and it actually does more complex models than what I talked about. So it's designed for psychological or behavioral applications where we might have clustering and repeated observations over time. So you can have random effects models that have random slopes in addition to random intercepts. And as I said, the textbook is a really fantastic resource. I think it's the one I would point people to learn about missing data and imputation. There are also a couple of non-free software options, M+ and RealCom Impute. M+ is not free, but it does have fantastic tech support. It is probably the least user-friendly of these, but if you get used to it, you get used to it. It has a lot of other capabilities as well, factor analyses, structural equation modeling, etc. And you can do multiple types of imputation there. And RealCom Impute, I personally have never used. It is free in the UK to UK academics, but not here. But it also does correct multi-level imputation using joint models. So I think that is pretty much right at time. So I'm happy to take some questions.
Thank you very much, Dr. Andridge, for that presentation. And we've got lots of questions, and we have some time for that. So terrific. One question about some of what you were talking about towards the end on R. Are there any statistical tests within R or SAS or Stata or any of these other packages that can help the investigator determine if the data is MCAR or MAR?
So
I'll stop there.
Sure. So the only one I know about is R. So there is something called Little's MCAR test. It's Little's because the person who came up with it was Rod Little, who coincidentally was my dissertation advisor. And it's essentially a multivariate test testing whether the MCAR assumption is appropriate. I think it might be implemented in SAS might actually have it. So it's Little's MCAR test. And it's basically doing what I've done here. Right, so I'm taking the people for whom I have the data, the people for whom I'm missing the data, and making comparisons on a bunch of different fully observed variables. And if there are differences, that's evidence against MCAR. So Little's MCAR test is a formal version of this that essentially gives you one p-value. here I don't need to run that test because it's very, very obvious that there are differences, and clearly this as well. But that's an excellent question. So Little's MCAR test is the test. There is not a test for anything else because you can't distinguish between MAR and MNAR.
Can you repeat the guidance that you gave about when it's appropriate to ignore missingness and use complete case?
Sure. Get back to the slide. Okay. So the first bullet here about MCAR, I put this on the slide because of course it's true that if you randomly lost 10% of your data, you're fine, but it's never MCAR. There's always something that is predictive of missingness. And so that's, most of the time we think about this regression situation. So the key idea is if you've got a regression equation and there are things on the left-hand side and things on the right-hand side. If the missingness is only in the things on the left-hand side, the outcome. So that's the way it is in a CRT most of the time, right? You lost them at follow-up, so you don't have their outcome. And this is true for individually randomized trials too, right? If the missingness is in Y and the things on the right-hand side of your equation are the things that predict the missingness, then you are okay. You don't need to use imputation. So in this example right here, this is the most commonly observed situation in a randomized trial, is that I lost some people to follow-up, so I lost some Y, but I observe everybody's treatment, and I have some baseline covariate, and those two things are what's predictive of the missingness. So for example, if you had differential missingness between the arms, right? So treatment group predicted how much missingness there was. Well, treatment group is in this regression equation. And let's say it was the baseline measure of the outcome. Well, if the worse you are at baseline, if you were more likely to drop out, as long as baseline is in the model, you're fine. So that it's limited to the situation of missing Y, and everything you need to predict the missingness is on the right-hand side of the equation.
Thank you. Does SPSS also have a multiple imputation utility, and do you have any comments about it?
Sure. So I am less familiar with SPSS. I get broad output from SPSS, but don't ever really run it. I believe that SPSS does do multiple imputation. I know that it's a little bit unwieldy, and I don't believe that they have multi-level imputation available. So it wouldn't be appropriate if you have any kind of clustering or repeated observations on individuals. It could have gotten better. They release a new version every year. It could be available now, but it has historically lagged behind Stata and SAS in terms of the big softwares and implementing imputation.
You've said that it is really important to use a congenial imputation model.
Mm-hmm.
And in some ways that means a friendly imputation model.
Yes.
I've always smiled when I saw that descriptor applied to data models. So this seems to be something that's really important. And I'm trying to make sure that I understand it correctly. If I include everything in the imputation model that I expect to use in the analytic model, is that safe?
Correct. Yes. Absolutely.
I can include more things if I want to, but
Correct.
The critical thing is to include everything in the imputation model that I expect to include in the analytic model.
Absolutely. So if this, what's on this slide, if this is your analytic model, right? Let's pretend X is the baseline Y. That's a common, right, ANCOVA style analysis. Then you could just impute using T and X to impute your missing Y, but you probably have collected some other data that's also predictive, so you can envision like adding those on here. So adding more is better. Well, many people would argue, because it kind of helps you get to MAR, right, in terms of the imputation, in terms of filling in those missing values. And so there's this everything but the kitchen sink kind of approach that is popular, as many things as possible that you have that you believe might be associated with the missing values.
Taken after the study is underway.
Dr. Murray, we're going to need to have you repeat that question.
Do I have to use only baseline measures in the imputation model, or can I use the first follow-up, the second follow-up, the third follow-up, and so forth, and the outcome is measured at the sixth follow-up?
That's an excellent question. You absolutely can use those things in the middle. So all those rules you have in your brain about what can predict what, right, in terms of causal and timing, kind of go out the window when it comes to MI, because we're just trying to get the strongest predictors. So you absolutely could predict Y at the sixth time point with Y at the fifth and the fourth and the third, et cetera, time points.
Multiple imputation can be used in the context of a linear model, a logistic model, a Poisson model, mixed versions of those things, pretty much anything?
Correct. Yes, there are specialized versions or flavors for different variables. Yes.
Effect modification. So you said that it was important to always include treatment in the imputation model.
Correct.
And then you said, but if you've got effect modification, you don't put treatment in the imputation model. You run it separately for the two arms.
Correct.
That seems contradictory.
So it's not contradictory actually, because if I separate the two, so if I run an imputation model and I just have a treatment group indicator, I have all the groups, both groups together in a treatment group indicator, and I'm also using something like the baseline value as a predictor, that is assuming that the effective baseline on the outcome is the same in the two groups. But what if it weren't? Then you would really need treatment group times baseline. But so you could run that model, or you could completely separate the two. So if you completely separate the two data sets, you're still essentially controlling for treatment. You're actually having every predictor be interacting with treatment by running two separate imputation models. So that's the reason for doing it separately, is you're basically buffering against in case the effect of baseline is different for the two treatment groups. If you impute by the two arms separately, then of course it's going to be estimated separately in the two different imputations. Does that make sense?
Okay. Yes, it does. How many variables do you need to put into an imputation model? Is there a rule of thumb or a magic number?
So there's definitely no magic number. I did not get into and talk about sort of diagnostics for imputation models, but there are some metrics. There's something called the fraction of missing information that tries to capture how much information recovery happened, right? How much did you get back? You can think of it as you're building a model. So those rules of thumb you have for how many predictors should there be in my logistic regression model, kind of similar for an imputation model. You know, if you have a small data set, you can't include a trillion predictors. But if you have a large number of individuals, you can include a pretty large number. You have to be careful about things like multicollinearity, or just like any regression analysis. The same caveats apply in terms of size of your model, right? If we have two very collinear predictors, they probably both don't need to be in the imputation model.
You've focused mostly on cluster randomized trials.
Mm-hmm.
There's a close relative, often called an individually randomized group treatment trial, where there are clusters in one arm usually and not in the other.
Right.
Does the guidance that you've offered here today apply equally to that kind of study?
It does. And in fact, for that kind of study, this recommendation is the easiest because then imputing in the treatment arm would require something that accounts for the clustering, like a random effects multi-level imputation model, but the control arm, you could just do the standard methods that are available in SAS and SPSS and Stata and right, all with no multi-levelness, right? Non-multi-level imputation is available in all the software packages. If you wanted to impute it all together, then what you would do is assign everybody in the control group to one cluster, so that you're still you're capturing the clustering, but then everybody in the control arm is in one gigantic cluster.
Sorry, it sounds like imputing separately by treatment arm is smart under a number of conditions. Are there conditions where it's not smart?
So I would say the only thing is for CRTs, or where you have a very small number of clusters, the standard congenial methods like a random effects imputation model are going to be challenging, just like they are for analysis. Right? If you only have 3 clusters in each group, in each treatment arm, and then you try to run a model with only 3 clusters. Those estimating those random effects, that's tricky. And so when you do the analysis, there are adjustments that need to be made, right? Small sample corrections in those adjustments. And so you kind of have to think about doing something similar with multiple imputation. And I would advocate for the predictive mean matching approach. So that's the sort of novel method that I have developed, which relaxes the importance of the estimates of the random effects in the imputation. So it's basically kind of trying to solve that problem of, but there's only 3 clusters. How do I estimate, how do I get the random effects for it? But I mean, aside from the sample size issue, this is very, very solid advice that I don't know, despite this fantastic paper, is not well known enough, I don't think.
Is there a reference given in your slides for this mean model that you just referred to? Predictive mean model?
Yes, it's where I talk about the congenial methods. Yes, this predictive mean matching adaptive for CRTs. Yes.
Okay, yes, Bailey et al.
Yes.
Okay. What about, there are variations on some of these models that we see from time to time. They're sometimes called cross-classified models or multiple membership models. Can we use multiple imputation when we've got those kinds of wrinkles?
That's a very good question. So I think it's a safe statement to make that if you can write down an analysis model that is correct for the structure of your data, you can do imputation from it.
Okay.
How easy it is going to be, how accessible that is as software is going to be tricky. And the more complex it gets, the more likely you are to end in a situation where it's intractable, right? If you have the best example of that is actually something where you maybe have multiple levels of hierarchy and you follow people over time. And it becomes really hard to correctly write down the underlying model for that data structure. But I think if you can write an analysis model and run an analysis model, chances are you can get an imputation from that model in some way. Depends what's missing, I guess I should say. If Y is what's missing, you can probably do it. If you have covariates that are also missing, it's going to be harder.
Do the methods for imputation change if the clusters are highly variable in size, or if the pattern of missing data is highly variable across the clusters?
So that's a very good question. I don't know of any work that specifically shows an answer to that question. I think that it's likely to be that the methods work better when there's consistency across the clusters, but it also depends a lot on how similar the clusters are. Like, what is the ICC? Because if there's not a lot of if the ICC is very, very small and you're doing the imputation, then it's sort of more okay to be borrowing strength from other clusters to impute if some clusters have more missingness than less missingness. But if you have a really high ICC, that can become tricky if you have very small amount of observed data in a particular cluster, right? Because then you just don't have a lot of information to impute within that particular cluster.
Our conversation today has been about randomized trials. Can we use multiple imputation in observational studies and in non-randomized trials?
Yes, absolutely. And I think it's more common in observational studies than it is in randomized trials because of this idea that the randomized trial, it has a pretty common situation where complete case is okay. But for observational studies, quite often it's not, right? We don't find ourselves in that situation where complete case is okay, and that you're going to end up with bias if you only look at the complete cases.
What if the team has used stratification or constrained randomization to balance the arms in let's say, a step wedge design? Do those features need to be reflected in the imputation model?
So yes, so the design features like a stratification would definitely want to be reflected in the imputation model. Yes.
This has been a terrific presentation, and I am grateful for the discussion that we've been having here with questions. I have not made a very large dent in the number of questions. They have just literally been rolling across my screen faster than I could read them, much less present them to you. But we are out of time. I will put together a list of all the questions that have come in, and we'll send that to you. And if you would be so kind as to offer thoughts on some of these, then we can post
Sure.
that online when we put up the slides and other materials.
I am happy to.
Terrific presentation. Thank you very much, and I'll turn things back over to John to close this out.
Thank you, Dr. Murray, and thank you to everyone who participated in today's webinar. On the Mind the Gap website, prevention.nih.gov/mindthegap, you will find several resources for this talk, including the slides and a list of references. We will also be posting a recording of today's webinar on our website in a few weeks. You will receive an email with a link to the recording when it's available. Thank you and have a great rest of your day.